Welcome to IGS 10-minute lecture series. This series is brought by the IGS department. IGS stands for Integrated Global Studies. In this series, a professor from the department will give you a mini lecture about her or his research area.
Hello everyone, this is Masumi Villeneuve from the IGS department. Today I'd like to introduce the world of interface science to you. First of all, interface is the boundary between two spatial regions filled with different matters. Here you see a piece of glass capillary filled with water, and from its tip a water droplet is hanging. In this slide, there are altogether three interfaces, namely an air-water interface, a water-glass interface, and an air-glass interface. Parallel to the interface, the force of interfacial tension acts. It is the tendency of an interface to shrink into the minimum area possible. In other words, it is the interfacial free energy. Although I'm not going into details now, the interfacial free energy arises from interactions among molecules comprising the matters. Objects of the same volume can have different surface areas. Between a cube and a sphere of the same volume, the sphere has less surface area. Thus, a round shape of a liquid is due to interfacial tension. This is a movie showing an interesting phenomenon caused by surface tension. The term surface tension is used when one of the bodies in contact is a gas or a vapor. Coins were placed on the water surface one by one. As the number of coins increased, they started to gather and stayed close to each other. Because surface tension tends to minimize water surface area between the coins. Eventually, the coins flock to the hexagonal closest packing. This experiment shows balance between pressure difference across a curved interface and surface tension. Now there are two bubbles of different sizes on the ends of a glass tube. They are separated by a stopcock in the middle of a glass tube. Could you guess what will happen when I open the stopcock and connect the two bubbles? Was your guess right? Let me leave the mystery for you to solve. Although we seldom notice, our daily lives are full of substances and processes that are under the influence of interfacial tension. Now I would like to address some features of substances in which interfacial tension plays significant roles. Such substances are called colloids. A colloid is a mixture in which particles of one substance are dispersed through a second substance. The particles of the first substance make up the dispersed phase, and the substance that they are mixed into is the dispersing medium or the dispersing phase. The general size of colloid particles encompasses about 10 to the minus power of 9 to 10 to the minus power of 5 meters. For comparison, the average diameter of a human hair is around 50 micrometers. In this diagram, the relationship between intensity and wavelength of light from the sun is shown. Large colloid particles have dimensions on the order of the wavelength of visible light, and they interfere with visible light. These are aqueous solutions of surfactant, a kind of soap, alcohol, and sugar. All samples have same ingredients, which are colorless per se, but in different concentrations, resulting in different colloid sizes. They have structures of sizes which are optimum to interfere with the visible light of particular wavelength. Such color is called structural color. Structural coloring is quite stable. Colors stay vivid as long as colloidal structures continue to exist. In fact, these samples have been in my laboratory for more than 20 years. Milk is a colloid in which liquid colloidal particles made of milk, fat, and protein are dispersed in water. It looks opaque and white because colloidal particles are about 2 micrometers, and they scatter visible light. Because these particles are of microscopic size, The total interfacial area between the dispersed particles and the dispersing water phase is very large. How large would that be? Let us think about the relationship between volume and surface area of a body. If I divide this cube into small pieces, the total volume will not change, but the total surface area will increase. And the smaller the pieces, the larger the surface area. The surface area of a cube that has 1 centimeter each side is 6 square centimeters. This cube is divided into 1000 cubes by slicing each side into 10 pieces. The total surface area will be 60 square centimeters. If the pieces are of micrometer size, calculation is done in the same manner and we get 6 square meters. This is 10,000-fold of the original surface area. Decomposition into nanometer size pieces enlarges the total surface area to 6,000 square meters. Properties of such colloidal mixtures are of course primarily determined by the chemical and physical properties of the dispersing medium and those of the particles. Moreover, the interfacial tension between the dispersing medium and the particles influences colloid properties. These are photographs from my studies on swelling mechanism of gluten-free, additive-free rice bread batter and show that the interfacial tension matters a lot. In the picture on the left-hand side, rice bread was successfully baked to give a soft and light texture. However, in the other picture, foams in bread collapsed. Chemical composition of the two loaves is same, however, the interfacial tension between starch granule and air is different for the two loaves. Isn't that intriguing? Finally, here are examples of colloids we encounter in our everyday life. Fog, smoke, shaving cream, whipped cream, dairy milk, paint, ink, activated carbon, jelly, gem opal, and so on. Well, this is all for now. I hope you enjoyed my lecture.